Hello, so in this video we're going to look at section 1.2, domain and range. There'll be 5 main topics that we're going to go over. Along with always, in the description below, there will be the video chapters, so you can jump to the various sections that you want to see. There'll be a link to the Openstax textbook, the first and second edition. There will be a shared folder that you're welcome to look at additional notes and resources for, and then there will be a survey at the bottom that you can check out. So first, we're going to look at interval notation, and for interval notation, we have the less than and greater than, and then we have parentheses or an open circle, which would mean that we are not included on our number line or in our graph. And then we have less than or equal to, greater than or equal to, or brackets, or a closed circle, and we would know that that is included. And then anytime you use the negative infinity or positive infinity, you want to make sure that's always in parentheses. So here are some of the cases that we may have. And so if we have x is less than a, we can see that a will go all the way to positive infinity. And so we can write it as an interval notation as in parentheses a comma infinity in parentheses. And so there will be various ways where we might have to include just a small section. So you would use the numbers for that given section. But if we go into infinity, we would need to list in parentheses negative infinity, comma, to wherever we're going, union with a number included or not, comma, infinity to with in parentheses. So next we're going to look at finding the domain of a function. So first, if we were given f of x equals 5 minus 2x, we can see that anytime we would plug in an x, we would have a real number. So our domain would be all real numbers. So negative infinity to positive infinity in parentheses. And so it would not matter. We could plug in a negative, we would still come back at a positive, and we would have a real number. It would not be imaginary, and it would not make the function undefined. So next we're given f of x equals this rational expression, and we want to know where it would be undefined because we want the domain. And so if we were to find out where our zeros are, we would know that if we have those values, it would give us a 0 in the denominator and it would be undefined. And so we want to exclude those from our domain. So if we put our denominator equal to 0, so if x squared minus 2x minus 15 equaling 0, and since that we can see x squared plus bx plus c form, we can go right to our factored, which would be x minus 5, x plus 3. And we can set those equal to 0. So we had x minus 5 equaling 0 and x plus 3 equaling 0. And if we were to solve for x, we would get x cannot equal positive 5 and x cannot equal a negative 3. And so we want to exclude those from our domain because that would give us a 0 on the bottom and make our fraction or rational expression undefined. And so for our interval notation, we would go from negative infinity to negative 3 in parentheses, because if we use a bracket, we're including it, and we can't use that value. But we can still have anything between negative 3 and a positive 5. So we would go union with, in parentheses, negative 3 to positive 5 in parentheses, but then we can still include the right side of 5, so we can go from union 5 to positive infinity. So next we're given f of x is equal to 3 minus the square root of 6 minus 2x. And so since we want to find out where it would be true or where it would be imaginary or give us a 0, we want to set our inside the radical equal to greater than or equal to 0 because we want everything on the right side of our number line. So we could do 6 minus 2x is greater than or equal to 0, and we can solve for x. If we subtract 2x from both sides, we get that 6 is greater than or equal to 2x, and if we divide by 2, we get that x is greater than or equal to 3. And if we were to flip it, we would get x is less than or equal to 3. And so we want anything on the left side of this number line where we cannot have. And so our domain would be negative infinity up to 3 including. And so next we're given f of x is equal to the cubed root of x minus 1. But since we have a cubed root, anything we plug in a negative, positive, it would still give us a real number. So we would always have a domain of negative infinity to positive infinity, or all real numbers. So next we have set builder notation, and it's not really a notation that I've seen a lot of classes use. So for interval notation, we can see that we can use a parentheses or brackets to show that it's included or not included, but it's very similar with the set builder notation where we have to set it in brackets with x, and then we're going to use a caret. We're going to draw a caret symbol, and then we're basically going to take whatever our and or statement is and put it directly into our brackets, and then we're going to close it. And so you can see that we have an and we can take our interval for in a notation. So we are going from negative a to a, and we can put it directly into our interval, our set builder notation. And we can do that for and we can do that for the or statements. So just as a reminder, for and, we want to make sure that both sides of our equation are true. So if we were given like x is less than 5 and x is less than 4, we would want to make sure that both of those statements are true, and we would make that correct. But if they were false, then it would not work. Or you could see where both of the number lines, if you graphed them separately, where they overlap, and that would give you an and statement. And for an or, we would want at least one condition to be true. So if we were given the same thing, we want to make sure at least one of the conditions were true. Where for and, we want to make sure that both conditions are true. We can see for and, where both conditions are true, and we have these top two where both of the number lines are going to be overlapping, showing that both cases are true, and so we would put that as our interval. Likewise for or, we want to make sure that one condition is true, and so we would have these bottom two, and typically they would go in opposite directions. So next we're going to look at finding the domain and range of a graph, and we want to give our answer in interval notation. And so in this, we're basically going to look at the graph, we're going to look at our x values first, and we're going to see where it's included to included or not included to included, and so on, vice versa. And we're going to list it in interval notation, and then we're going to do the same thing for the y values. We're going to look at the graph left to right for x values, and we're going to look at the graph from bottom to top for our y values and see where our graphs would be. So if we were given this graph, we want to see what our domain and our range are. So for our domain, we would look at our graph and read it from left to right. So we can see that we're including -4 and we're including a +4, and so our domain would be in brackets -4 to +4. And for our range, we're going to be reading it from bottom to top because we're going negative to positive. So we're going to read it from bottom up. And so we can see that we're including 0, then we are including 1. So our interval notation would be in brackets from 0 to 1. So next we're given this graph, and we want to find out what our domain and our range are. So for our domain, we know that we're going to look at it from left to right. So we can see that we're including a +5, and then we're including all the way up to a +3, but we're not including a +3. So our domain would be including -5 up to a +3. For our range, we know that we're going to be looking at it from bottom up. So we can see that we're including 0, but then we're not including 2 because we have it included on one side, but it's not included on the other. so we would not include it. And so our range would be in brackets 0 to 2 in parentheses. So next we're going to look at piecewise functions. So for a piecewise function, it's more or less using different variants or different domains for each one. So we're going to give typically 2 or 3 different formulas, and then each one will have its own domain. And so if we look at it for a graph, we would make sure that if we're using this value, where does it fit our domain, and that would be the formula that we use. So now we're going to want to write the piecewise function based upon the graph. So for a piecewise function, we want to make sure that we're looking at it from left to right. So we can see that for this first chunk, we're at -9, -8, and we are going over to -5, 8. And so since we're looking at domains, we would put for our first domain, for our piecewise function, we're going from -9. So -9, we're going less than x and then less than -5, what we're equal to, because we're including our -5. So then if we look at our next section, we're up here, and we're going from -5 to a +1, or to a -1, and we can see for where we equal 6, we are going from a -5 less than x less than or equal to -1. And then if we look at our final section, we can see that we're going from -1 not including, and we're going all the way over to 9 including. So at -7, we're going from -7 is less than x is less than or equal to 9. And that would be our piecewise function for this given graph. So now we want to graph a piecewise function. So we're given this piecewise function, and then for the top, we can see that our domain would be x is less than 1. So we want anything from -infinity up to 1. But then for the second one, we want x is greater than 1. So you want anything from 1 to +infinity. So if we put So if we were to put an open circle on 1, we could draw just a graph. So we're going positive this way, and we're including, but then we're also going this way, and we're going to include that as well. And since they're both quadratics, we would just get a parabola, and we would put our domain as -1 to -infinity to 1, not including union 1 to +infinity. So now we want to evaluate for f of -1, f of 0, f of 2, and f of 4. And so for the first one, we have that f of x is equal to, in our piecewise function, x plus 3 and x minus 6. And x plus 6. And so since we would want to follow wherever these points lie, we could look at f of -1 first. So for f of -1, if we were to look at our functions or our domains, we would see that our -1 lies in this top function. So we would take 7 of -1 plus 3, and we would see that it would equal -4. We can look at f of 0. We can see that it lies in the bottom for x plus 6, because it's in that domain. So we would take 7 times 0 plus 6, and we would just get a 6. We can look at f of 2. We can see that it is in our x plus 6 domain, so that's the equation we'll be using. So 7 times 2 plus 6. If we look at the f of 4, we can see that it is in our x plus 6 domain, and so we would take 7 times 4 plus 6, and we would get a positive 34. So next we're given this piecewise function of f of x, and so if it helps, you could put the domains for each of those piecewise functions next to them, so in interval notation, if it helps you. So first we want to find f of -1, and we can see that f of -1 would be in our 4x plus 5 domain. So we can use the 4x plus 5, use our our function. We can go f of -1 is equal to 4 times -1 plus 5, and we can see that we will get a 1. Now we want to find f of 0, and we can see that f of 0 would be in our 4x plus 5 domain. And so we would take 4 times 0 plus 5 and see that that would give us a 5. We can look at f of 2, and we can see that it would be in our 3x minus 8 domain, and we can do 3 times 2 minus 8. And if we were to plug that in our calculator, we would get a -2. So now we want to look at f of 4, and we can see that 4 would be in our 3x minus 8 domain. So we would do 3 times 4 minus 8, and our answer would be 4.